There we go, back to it. So we know that because we set the denominator equal to 0, we know this is a vertical asymptote because it doesn't also make the numerator go to 0. All right, now let's find any horizontal asymptotes. Or Haas. This will occur, or remember, we need to compare the degree of the top to the degree on bottom. The degree on top here is 2. The degree on bottom is 1, because remember, there is secretly a first power on this x. Even though it's not stated, that is the case. And so, remember our rules for horizontal asymptotes. We compare the degrees on top and bottom. I'll go through it again real quick. If the degree on top is greater than the degree on bottom, you're going to have no horizontal asymptote. The reason behind that is a horizontal asymptote is kind of like a value that the function is trying to approach but can't ever quite get to. In other words, it's almost like you're cutting it off after a certain amount. You're limiting its potential. But when the degree on top is greater than the degree on bottom, the numerator is just going to blow up faster to infinity as you insert larger and larger x values, and the bottom won't be able to keep up. So the whole thing is going to blow up to infinity and is not going to be bounded like that. You're not going to be able to put any like limitations on it. When the degrees are the same, whenever the degree on top equals the degree on bottom, the horizontal asymptote is the horizontal line, y equals, and then it's the ratio of the top coefficient, lead coefficient, to the bottom lead coefficient. And then whenever the degree on bottom is strictly larger than the degree on top, your horizontal asymptote is going to be the line y equals 0, which is also the x-axis. But for our case here, the degree on top exceeds the degree on bottom, so there's no horizontal asymptote to worry about. But you still need to check for it. Still need to see about that. Finally, oblique asymptotes, or the OA. These occur when the degree on top is exactly 1 more than the degree on bottom. Which is the case here, like we already said. How do we figure them out? Well, technically, we need to actually do the division. To figure out the oblique asymptote, it's going to be a line in y equals mx plus b form. You find it by actually dividing the top by the bottom. In other words, technically you can do the polynomial long division here. And let's just use the line tools. Technically you can do the polynomial long division, which would look something like this, but this can get a little bit hairy. Instead, let's just use synthetic division. It's the same thing, except it's a lot easier to deal with. So our denominator is x plus 3. So remember, with synthetic division, we put a negative 3 into a box here. And along here, we put the coefficients of this. It's going to be 1 for x squared Now it skipped over an x term, but whenever we're doing the division, we need to include then a coefficient of 0 for the x term. And then finally minus 4. And so we do the synthetic division, bring down the 1. Negative 3 times 1 is negative 3. Zero plus negative 3 is negative 3. Negative 3 times negative 3 is 9. Negative 4 plus 9 is 5. And that's going to be our remainder. And we're actually going to ignore it here. And we'll just make the line y equals, this would be 1x, or just x, minus 3. And that's going to be our oblique asymptote. Let's do one more. Let's try a different one. And we'll go a little bit faster with it. How about we do seven x squared plus 7 over x squared plus 6. Let's find any asymptotes that this one has. So we'll start with VAs, vertical asymptotes. Well, we're going to set that denominator equal to 0. And what we're going to see, maybe you already see it, you've got x squared, which is always going to turn out positive, no matter what real number we put into it, positive or perhaps 0. So this thing will never go negative, but then we're adding 6 onto it, so it's never going to get all the way down to 0. And to see that, move the 6 over, and it's going to have to be x squared equals negative 6. Apply the square root property where we take the square root of both sides, and then there's the plus or minus, but that's not going to matter because we're taking the square root of negative 6, which in turn means that our little friend I is going to have to pop out of there. Plus or minus square root of 6, and then an I taken out. But whenever you involve I, you're not talking about real numbers anymore. And whenever you're talking about vertical asymptotes, you're talking about the graph. And the graph only wants real numbers. It only wants real numbers. You can't graph complex numbers on a standard coordinate plane. So my conclusion then is that there are no vertical asymptotes. There aren't any. The denominator is never going to go to 0 for any real x values. Okay, that's convenient. Horizontal asymptotes. I don't want it blue, I want it green. There we go. Horizontal asymptotes. Now, remember there's the three cases. You compare the degree on top with the degree on bottom. The degree on top is 2. The degree on bottom is also 2. So when they have the same degree, the horizontal asymptote is the ratio of the lead coefficients. Now let's see what that actually looks like. It's going to be y equals, and it's got to be y equals because it's got to be a horizontal line. The lead coefficient on top is 7. The lead coefficient on bottom is an understood 1. Those are the lead coefficients, and it's a ratio of them. It's going to be 7 over 1, or just the line y equals 7. So that's going to be our horizontal asymptote. It's just a horizontal line crossing the y-axis at 7 and then continuing on in both directions. If this had been a, I don't know, if this had been an 11 down here, then the horizontal asymptote would be 7 over 11, 7, 11, which is still a horizontal line. It's just fractional, and it's a little uglier. So take from that what you will. So no horizontal, no vertical asymptote. We've got one horizontal asymptote. Finally, oblique asymptote. There won't be an oblique asymptote here because that again only occurs when the degree on top is exactly 1 larger than the degree on bottom. So we've done it. There's only one asymptote to this rational equation. It's a horizontal asymptote, the line y equals 7. So that's going to be it for chapter 3. We do, just for the sake of time, we do need to get a little bit of a start on chapter 4. Now, keep in mind that chapter 4 is not going to be on your next exam here, but it'll be on the one that's right before Thanksgiving break. So this won't show up for a couple weeks as an exam, but it's just for the sake of time. We have to just kind of do it. The section 4.1, we're actually going to get into, in chapter 4, we're going to get into new types of functions. We've looked at polynomials. We've looked at how to graph polynomials. We've zoomed in closely on quadratic polynomials, second degree polynomials, and we looked at their specific properties. We've looked at first degree polynomials, which are just linear functions, lines. But we haven't kind of investigated all the different exotic types of functions that exist in the world. Well, we're going to remedy that today. We're going to, or not today, but with chapter 4, we're going to look at some exponential and logarithmic functions, we call them. And we're going to see what some of their properties are and what makes them so special. That's about all I'm going to say about that. Well, actually, one of the interesting things about exponential and logarithmic functions are that they are inverses of each other. They are inverses of each other. What does it mean to be an inverse? Well, I'll show you. So let's make a quick definition to start with. A function f of x is called one-to-one. If whenever A is not equal to B, then F of A is not equal to F of B. And that is a very fancy way, an incredibly fancy definition. In other words, two different x values, which we're just calling A and B, two different x values cannot produce the same y value. Now you'll recall we defined what it meant to be a function. We defined what it meant to be a function earlier in the semester. It had to pass a vertical line test, and it said that a single x value can't produce two different y values. Now we're putting an extra, now we're going to put an extra kind of imposition on it and say, well, we also need to look at the case where two different x values shouldn't produce the same y value. It's kind of like the opposite reasoning of that. So there's a lot of interesting things with being one-to-one. Earlier, we talked about a function. Let me draw a simple graph. Passing something called the horizontal or the vertical line test. So let's see. Let's make something that looks kind of like a cubic function here. And what we did was we said it had to pass the vertical line test. If we could run a vertical line across it, like so, and if that vertical line never touched the function more than once, it passes the vertical line test. Well, we can see that this function here in red does pass the vertical line test. This passes the vertical line test and thus is a function. However, now we also need to talk about a horizontal line test, so to speak. Make it nice and long. Now we need to do a horizontal line test. We basically need to scan the function kind of up and down. And what we see is that if there's ever a moment where the horizontal line crosses through the function more than once, this fails the horizontal line test. And we see that it does that here. It does that, in this range of values here. So this actually, this fails the horizontal line test, and thus this function is not one-to-one. So it's still a function. We can still analyze it. It looks an awful lot like a cubic function, but it's not going to be one-to-one, which is just an extra property that we are going to investigate. So what does it mean to be one-to-one? Well, look, whenever it hits here, these three different x values. There's this x value down here. There's this x value right here. And then there's this x value right here. In this case, there's more than one x value that all produce the exact same y value. That all are going to produce the exact same y value. And so just by the straight definition of what it means to be one-to-one, it's not going to be one-to-one. It's going to fail to do that. Why do we care about things being one-to-one? Well, what we really care about is the fact that when something's one-to-one, it's going to have what we call an inverse. It's going to be invertible, in other words. And so that's kind of what we want. That's a good thing that we're trying to get at. It doesn't always happen, though. And so only in special cases can we actually even talk about the inverse of a function. But we want to. We want to talk about it. So let's look at another example. Let's look at an actual defined function. Is the function (25 minus x squared) but inside of a square root? Oops. Is this one-to-one on its whole domain, on the entirety of its domain? Well, that's the million-dollar question. Now, it's hard to say exactly without maybe looking at the graph, but we also haven't exactly looked at how to graph something like this. Or it turns out it kind of will be something we could graph in theory, but we're not quite going to go that route. Instead, what I'm going to say is, well, if we can think of two different x values that produce the same y value, this will not be one-to-one. And just from pure reasoning, we see that we have an x squared term in there. We see that we have an x squared term in there, which is nice. That's going to kind of give it away, because I know that if I plug negative values into x squared, they're going to become positive. If I put the same positive value into x squared, it's going to stay positive and it's going to become the same number. So actually, we can just think of maybe two x values that are just negatives of each other, and that's a good guess. So why don't we try x equals -3, and let's try x equals +3. Let's try those out into the function. So we're going to find f of -3. We need to figure out what their y values are. You put a -3 into this function, you're going to have square root of 25 minus -3 squared. And we just work out the math a little bit. -3 squared becomes +9. 25 minus 9 is 16. So we're just left with the square root of 16, which is 4. So an x value of negative 3 produces a y value of 4. Because when you plug it into the function, you get 4. As it turns out, you're going to notice the exact same thing whenever you plug in x equals positive 3. In fact, that's the whole reason we tried it out. That was the whole guess behind it. And that's actually why we picked them, because even though one was negative, one was positive to start with, by squaring them, you're going to wipe that out and end up doing the exact same process in the long run. So x equals 3, y equals 4 whenever you do that one. So the takeaway is this. We found two different x values. Negative 3 and positive 3 are not the same, or they are, they're two completely different x values from each other. But whenever we plug them in, whenever we try them out into the function, they produce the same y value. That's going to be the problem. So we found two different x values that produce the same y value, not t. Thus, f of x is not 1-to-1. Thus, f of x is not 1-to-1. Now, if you had a function that you suspected was 1-to-1, and you wanted to see if it was 1-to-1, does that mean you have to go and try out every possible x value and make sure that you're not getting any repeated y values? I mean, theoretically, yes, but that's actually just where graphing is important. That's where you want to understand the way things are graphed if you wanted to prove it was 1-to-1. So we're not going fully 100% all the way in depth with inverse functions. We're just kind of taking a little bit of a light look at them to start with. So now a little clue we'll learn in a moment. I'll just kind of preview it now. When two functions, when a function is 1-to-1, you can take its inverse. You can take its inverse. So inverse functions, they are two functions that basically undo the effects of one another. That's a good kind of simple definition for it. One kind of does the opposite of the other. So for example, let's say you had two functions, f of x equals 8x plus 5. And let's say you had g of x, a g of x function, 1/8 x minus 5/8. Well, we're going to find out that these just might be inverses of each other, but we can't see it yet. But let's try this. Let's plug x equals 10 into f of x. Let's just play with it a little bit. We're going to do that, and then we're going to plug what we get from that into g of x and see what kind of magic happens. Okay, well, f of 10, it's going to be 8 times 10 plus 5, which is going to be 80 plus 5, which is going to be 85. So this is how the machine works. We're going to take an x value of 10. We're going to plug it into the function f. Whatever we get from that, we're going to take this now, and we're going to plug it into g of x. So we're going to look at what g of 85 is. Well, okay, just plug it in. Well, let's see. We're going to get 85 over 8, essentially, minus 5 over 8. Well, they have the same denominator, which is nice. 85 minus 5 is just 80. So we end up with 80 over 8, which is 10. Wait a minute, that gets us back to what we started with over here. That gets us back to what we started with. So here's the process. We plug 10 into f of x, then plug what came out of that into g of x, and got back to 10. So f of x and g of x kind of undid each other's effects. Now that was only for one particular x value. Who knows if that's going to be true for every x value on the planet? That may not be the case. But it turns out that in general, it actually is going to do that. And so what we're going to see is that these two functions are inverses of each other. They are inverses of each other. Because one undoes the effects of the other. So let's formally definition of inverse functions. Let f of x be a 1-to-1 function. So the only way you're going to be able to take an inverse is if you're starting with something that is 1-to-1. That's going to be the only possible way. So let's let f of x be a 1-to-1 function. If that's the case, then g of x is the inverse function to f of x if, basically, if you can plug them into each other and you just produce an x. So if you use function composition, if I plug g of x into f of x and it produces just x, it produces like as if I had just plugged a number in and it produced itself. And I'll just put this here, but we're not going to harp too much on this detail. If I can plug one into the other, and I can go both ways with it. And if I can put f of x into g of x, and it just produces x. Because think about the process, f of g of x. So if I put a 3 in here, that 3 first goes into g, and then whatever that produces goes into f, but then it's supposed to come all the way back and just produce the original 3 I plugged in to start with. And same if I go the other direction, if I put f of x into g of x. This is what it means for them to undo each other's effects. We just start back with the original term we plugged into them. So this is actually kind of powerful here. This is going to be our straight up definition. This doesn't yet quite tell us how we can actually find inverse functions, but it does give us the roadmap for doing it. It does kind of show us it's the definition, which is important. And it's going to actually give us a bit of a roadmap for actually finding inverse functions of each other. So let's do this. Let's see if I can make this smaller. And so I can keep it on the whiteboard. I bet I can craft away. It doesn't want to work. That's fine. We'll just move it kind of up and out of the way. We'll keep it in mind. And so now let's try an example. Are these two functions are x cubed minus 1 and the cubed root of x plus 1, are they going to be inverses of each other? Well, they're only going to be inverses of each other if I can plug the g of x function into the f of x function and just get x. And if I can plug the f of x function into the g of x function and just get x. Now, it's actually implied that, excuse me. It's actually implied, though. Remember, you have to have that you're starting with a one-to-one function. But it turns out if you look at the parent function of x cubed, it does pass the horizontal line test. And if you just move it down 1 unit, it'll pass the horizontal line test still. Here, the parent function for the cube root of x would also have passed the horizontal line test. And then all we're doing is moving it to the left 1 unit with this, which doesn't change its ability to pass the horizontal line test. Although in general, a third degree polynomial is probably not going to be going to pass the horizontal line test and be one-to-one. In this case, this particular one is. So the way we're going to do it, well, we got two things to compute. We have to find f of g of x, which remember, that's going to be where we plug g of x into f of x. So we need to take this whole business right here, this cube root of x plus 1, and plug it into f of x. So it's going to look something like this. We took this here and we plugged it into x from the f of x. Now you're looking at that, but you'll notice the cubed root here is then being cubed. Those are actually opposite operations of each other. Cube rooting something and cubing something, they undo each other's effects. So all we're left with is what was inside that, x plus 1. And then we had this minus 1 out here. And when you combine like terms, you just end up with x. So we can check this part off. Okay, f of g of x works. It does what it's supposed to. Now we want to go the opposite direction. We want to do g of f of x. We want to plug our f function into our g function everywhere we see an x. So the overarching function is going to be the cubed root of, then we plug this business here, x cubed minus 1, and that's been plugged into x, and then we're adding 1 yet onto there. Now we have minus 1 plus 1 going on in this inside of the cubed root. They're going to cancel each other out, basically. And you're going to be left with the cubed root of x cubed, which again, those are opposite operations of each other. And you're just going to be left with x. Which means that this second case is also satisfied. So yes, f of x and g of x are indeed inverses of each other. They kind of undo each other's effects. That's kind of the long and short of it. Okay, so that's almost done with the first section of chapter 4. I think that's good enough for today. We got a nice little jump into chapter 4, a little head start. Let's spend the rest of the class reviewing. Let's do a little bit of a review with the rest of our class period. What I'm going to do is I'm going to open up your exam 3 review, which has been open on MyLabs Plus for you for a little while now, since before the weekend. And I'm just going to kind of pick a few problems and work them. If you guys have any questions, conceptual questions for me, feel free to shoot me a question. Whatever you think is best. If you just, I don't know, I guess shout into the computer or something. and let me know. Otherwise, I'll just kind of hand pick a couple of questions and we'll work through them. Does that sound good to you guys? I hope it does. I can't hear anything if it does. So let's see. Let's talk about the vertex of a parabola. So this one wants us to identify the vertex of the parabola y equals 2x squared plus 8x plus 5. Two x squared plus 8x plus 5. Let's review a few quick things about the vertex. The x coordinate will be, it's got that weird little formula, x equals negative b over twice a. And then the y coordinate is found by plugging that x coordinate into the parabola, into the function. And so what is b, what is a? Well, remember those are the coefficients. This is going to be your a. This positive 8 is going to be your b. And then technically the constant is c, although we don't care about that in this particular problem. So the x coordinate is going to be x equals negative b, so negative 8 over twice a. A is 2. So it's going to be negative 8 over 2 times 2, negative 8 over 4, negative 2. We're not done though. The vertex is a point on the graph. So you better write it as a point with an x coordinate and a y coordinate. Now the x coordinate is kind of the heavy lifting. The y coordinate, we're going to plug this x coordinate into the function. And kind of see what shakes loose here. We'll do some of the algebra. Eight minus 16 becomes negative 8 plus 5 becomes negative 3. So we've got the x coordinate and the y coordinate of the vertex. So the vertex is the point negative 2 comma negative 3. Pretty straightforward. Let's try another one. This is going to be a synthetic division problem. Let's see. 2x cubed plus x squared minus 3x plus 2 over x plus 3. We'll use synthetic division to do this one. And then we'll write out kind of what it does. And what will normally happen is if there's no remainder, it's really nice. We can just write it out cleanly. If there is a remainder, we have to do a little bit of an adjustment to make that happen. So let's see, synthetic division, we're dividing by x plus 3. So for the synthetic division, we're going to put a negative 3 up here in the top left corner. Along the side, we're going to write the coefficients in descending order. You're going to have 2, positive 1 for the x squared, negative 3 for the x, and then 2. So we're going to bring the 2 down. We're just going to do the synthetic division now. Negative 3 times 2 is negative 6. One plus negative 6 is going to be, well, it's the same as 1 minus 6, so negative 5. Negative 3 times negative 5 is positive 15. Negative 3 plus 15 is going to be 12. Negative 3 times 12 is going to be negative 36. 2 plus negative 36 is like 2 minus 36. It's going to be negative 34. So this is going to be our remainder. And so all told, what you're going to be left with, we have coefficients down here. We started with a third degree polynomial. We divided out this, so we're going to be left with a second degree polynomial. It's going to look like this: 2x squared minus 5x plus 12. But when you have this remainder, you need to express it like this. And so that is what we are going to have. That's going to be our answer. Before I go on to another problem, do you guys have a specific problem or concept you'd like me to review?
Anybody have something specific you want to go over?
A specific problem or concept? This is chapter 3 material, so this will be for the exam.
Yeah, what are we struggling with? I don't know. You're asking me the most about graphing rational functions, right?
What's that?
It sounded like from the little bit I've been helping, like graphing rational functions has been kind of the hardest part.
Okay. Let's look at it.
What did you say?
Let's see if I can find one here in the review. Let me see. Well, what I can say, some good news is that I think it's important for graphing rational functions just to kind of identify what the different asymptotes are. Though on the exam itself, there's just straight up not going to be a problem that's going to ask you to graph it by hand or anything, to graph it by hand. At the very worst, there might be one where you just have to look at it from the asymptotes, but I don't even believe there's one of those on there.
The poll's going to be on there.
What's that?
Our poll's going to be on there.
They might. So yeah, do we want to work one that's going to have a hole? Yeah, I think that's a good idea. Let's work one that could have a hole involved. So yeah, let's graph one, and you're going to see it's not going to be as bad as it looks on the surface. Let's graph x squared minus 16 over x minus 4. Well, if we can tell it's rational, we have the ratio of two polynomials, second degree polynomial divided by a first degree polynomial. So once you know it's rational, you already know you're looking for asymptotes. So let's start off with any vertical asymptotes. Well, the only potential candidate for vertical asymptote, we would set the denominator equal to 0. And when we solve for x, we get x equals 4. So we would think this is a vertical asymptote, but we need to make sure it's not a hole. We do that by plugging this value into the numerator. We plug it into the numerator, and actually what we're going to find out is it will be a hole. So actually, x equals 4 made the top and bottom go to 0. So it's actually a hole. This actually creates something interesting whenever it's a hole, because if it's a hole, let's think about it. It made the bottom go to 0, it made the top go to 0. That means for just the bottom polynomial, it was a root of it. For the top polynomial, excuse me, for the top polynomial, it was also a root of it, which means furthermore, if we were to factor the top and bottom, we will actually get the same factor on top as we will on bottom. So this one's actually going to have a little twist to it. Let's try factoring that numerator. We have x squared plus 0x minus 16. So technically we have x squared plus 0x, and I only write that to help us factor it. Or you can see it's a difference of squares. It's going to be x squared plus 0x minus 16. So we need two numbers that multiply to negative 16 but add to 0. And that's going to be x plus 4 and x minus 4. And on bottom, you're going to have the x minus 4 here. So look what happens. We get cancellation. The x minus 4 factors can cancel with each other. Now that doesn't mean, though, that this hole we found is no longer an issue. It's still an issue. So the hole, not W hole at x equals 4 is still in play, though. But otherwise, we just have the line y equals x plus 4 with a hole when x equals 4. So
now we're going to plug in 2 right here. 2 minus 1.
If we look at the graph, simple XY graph. It's going to have a y-intercept at 0, 4. It's going to be a positively sloped line. It has a slope of positive 1. So it's going to look something like this.
Hey, cool. Somebody left me a MacBook. What's your computer? I'll love a MacBook.
It's going to have a hole on the graph when x is equal to 4. It's going to have a hole in the graph right here. Something like that. So otherwise it looks like a regular line because we were able to do the division, cross out factors, but it's going to have this single hole right here. But what I will say is that actually fully graphing rational functions is just not going to be something that's going to be on the test. You know, just say that it's just not going to really be on the test. But identifying their asymptotes is going to be something that's on the test. So do you guys have any other questions? We have about a minute and a half. Let's see. Just keep in mind that the domain of a function is all x values that you're allowed to basically plug into the function, all valid x values. And the only thing that is going to disqualify an x value is if you try to divide by 0. So any x values that cause you to divide by 0 is not in the domain. In fact, you can see from this graph, there was a hole at x equals 4. So x equals 4 is not in the domain of that function, of that rational. The only other issue with domain is if you try to take the square root of a negative number. So you need to throw out all x values that would cause you to take the square root of a negative number.
Quiet. Be quiet.
And then for any polynomial, anything that's a true polynomial, its domain is the entire real number line. So I would really keep that in mind because domain is something that could very well pop up on the exam. So it's 9 o'clock. Y'all have a good day. We'll see you Thursday morning.